Greetings, gentle readers, fellow earthlings. This is the way I usually start these videos. Reading foundations today. Reading foundations of reason and logic, mathematics, physics. Reading foundations today, which is July 29, 2026, with Ross Finlayson, myself. We'll be just kind of following along in this box of books, and then even getting through it, as there's not quite so many left, or as such direct relevance to the theory, like Leibniz's philosophy, Leibniz, the accounts of the principles of reason and what makes for logic and the total. I'm reminded, or I thought I'd mention a couple videos on YouTube that I watched recently. One of them was a sit-down conversation of Brian Greene and Carroll. So Brian Greene is a well-known popularizer of physics in his books first, and later this was from this World Science Festival, or his production company. This talk set in a library of two easy chairs and a glass of water at the ready, to have that doctors Greene and Carroll had a chance to talk about the deep mysteries of the foundations, and foundations was mentioned several times, and the importance and the centrality and the priority of foundations. So what I derived from this conversation was that while at once it was their usual talking points, as they may be, as with regards, for example, to accounts of standard physics, and then with regards, for example, to their particular interests like string theory or multiple worlds, was that the speakers had refinements and retrenchments and even apologetics, in a sense, to their stated and standing opinions about what was relevant to them, and their perception and the meaning and belief of these things, that it gratified me to see the maturation, to see the improvement, in a sense, of kind of their opinions on these matters, where I could find it more agreeable, is what I intend to convey here. So, for example, there was, with regards to the Everettian or multiple worlds hypothesis in quantum mechanics, it was talked away a bit. Then it was quite a bit more about the random indeterminacy, and not so much the realization of the non-scientific multiple worlds interpretation of parallel worlds. That the chance and uncertainty and indeterminism still exist with regards to Heisenberg and then Schroedinger. Yet it wasn't taken further afield to where that was kind of the milieu. So that seemed then that Carroll has improved that by saying less about what it was, and so that their followers would be less likely to trap themselves in non-scientific reasoning or just fallacies or the incompletions as complete in these sorts of things. And then with regards to Greene, it gratified me that, for example, it was framed that it was general relativity, not special relativity, that's primary, and GR first, in a sense. And then also that the accounts of the reasonings for why string theory, which is here, it's basically that after world lines and then for particles and then world sheets, or the strings, their lattice, their web, their milieu, their composition, that superstrings are just as smaller than atoms as atoms are smaller than us, is the idea here. And then that the not that that's necessarily the usual idea of superstring theory with regards to strings and stringlets, as they were, the Poincare stringlets, as it's put here. That it gratified me that first there was a setting more in the absolute, and then as well that there was more focus upon the matters of the completions in the classical and the continuous. So when one of the speakers, for example, made a point about halfway through of like a 2-hour conversation that they had, that it was about infinity. And so after matters of kind of backing away from the shut up and compute aspect of physics, and then describing himself as a philosopher now, that infinity was still rejected. There was kind of an aversion and repulsion of it. Yet it's still that continuity is key. And so continuity with regards to invariance and symmetry-breaking instead symmetry-flex, and continuity law instead of conservation law, so that things just don't break everywhere. With regards to the discontinuous, has that infinity is still in the continuity. And so when talking about how that it's bane to mathematics, here there's real mathematical infinity as after the natural infinities and the natural continuity bit. And so then for accounts of the universals and the sui generis, it has that subject its own deconstructive account. So this is where, when talking about things like it was not mentioned or inargued about the Big Bang vis-a-vis the steady state hypothesis, and the fact that neither of those are falsifiable and both of those fit the data. That was considered not quite a more thorough sort of awakening or realization of what the reality of what the things would be. That a lot of the talk was about reality and belief, and then the laws of physics vis-a-vis axioms and principles and the like. Then it also kind of gratified me that one of the accounts of Dr. Carroll was that in his schooling, and where he's a pronounced and well-known atheist in this sense, and so he described, though, that in his schooling that basically he studied religion, or he took a lot of religion classes, as he put it, before. And so what that means is, and then as he put it, that he was very familiar with the arguments either way and both ways. And so this kind of gratified me, because instead of kind of making for an exclusion of the fact that, again, more of the unfalsifiable, the non-scientific matters of truth and belief, the absolute, that even as from the stance of an atheist vis-a-vis the agnostic, which is the proper sort of scientific course, then with regards to there's freedom of religion, and then with regards to atheism is a religion, it's what people bind themselves to make their meaning of belief. It's certainly acceptable that then the account was framed as being for a personal interpretation of things. And so then both of them at least had in the accounts that they had their own free will, and that the free will is a thing among thinking beings. And then also it was gratifying then that for after the accounts of the sui generis and the ineffable, and then besides for infinity, that then there was mentioned de Broglie and Bohm, or de Broglie, if that's how it was pronounced. I will just say de Broglie because that's the phonetic reading according to the English transliteration of de Broglie. And here in that Musitorium playcast, you can see an interview with de Broglie en français about waves and particles, with de Broglie on the side of the wave mechanics after Schrodinger. And then the account that there was a continuity involved. Then also the notion of the spiral and the vortices. It wasn't so much mentioned that for the wave and the spiral vortices, after some mention of Kelvin and the like, for the statistical ensemble and some quotes of Kelvin, then that these can be read in the wider sort of account as making for wave spirals and spiral waves and frame spaces and space frames. Then that the mathematics of natural infinities and continuities is owed to physics. And then that it would automatically equip physics, the models, for the differences between the partial accounts and the total accounts, and including the relative or relational or relativistic accounts, the absolute and the total accounts. So that, I thought, is just a comment that it is an improvement in my perception of those opinions, which otherwise I kind of poke as either closed or wrong. So that's just said that that's something that I thought was an improvement, and it helps to reflect the zeitgeist in the study of physics about what's philosophy is supposed to mean, that it's about structural realism. So structural realism then is the account of that it exists, and we are in it, and it's real in these sorts of accounts. So I was watching this talk, and it was this fellow named Kahle, I think his name is Kahle, and he studies structure, that would be Struktur in Deutsch, or in German, but it was in English, this presentation and discussion at a French institution en français. So what he's about is the structure, and who he was talking about were Poincaré, Hilbert, Bernays, and Gonseath. And so Poincaré is a famous geometer, and Hilbert is known for Hilbert's program. Bernays is a philosopher of mathematics, again in the same sort of time as Hilbert, but about the 1930s. And then Gonseath was also a rapporteur, or a theorist of lesser known stature, but as of this time, Gonseath, Gonseath. So what he got to talking about was the difference between the schemified and the structural. And then as for axioms and model theory, and about parameters and variables and terms, and then the account of induction and whether it's complete, and the question of the weak and strong induction, and then as was mentioned, Aristotle and the potential and actual infinity, and the account from Kahle that, for example, the usual law of large numbers is the law of small numbers, and incomplete, weak induction. And that's for the whole questions of empiricism and these sorts of things. That it gratified me that a reading of Kahle's comments would, generously read, be more along the lines of what Leibniz makes for idealism, and what Poincaré makes for idealism, and these absolutes, or the totals, that the schemified varieties, or axiomatizations, and then the structural accounts, or for the models in the model theory, have that. What was missing, though, was a sort of disambiguation of the schemified in the structural, and the structural in the schemified. Because accounts of model theory, and here model theory and proof theory are equi-interpretable, what can be said in one, it can be said or shown or demonstrated in the other one, has that proof theory after axiomatics is kind of in the language of words. And model theory with the structural realism is all the model. And so model theory in axiomatics is just schemification in the structure of words. But structural universes are all the model. And so the disambiguation there is to make for the accounts of the different lenses and the interpretations of those. And then it's similarly for the parameters and the invariants, and the cases for induction and the cases for completion. And then the reading Poincaré's comments as after those make more for so why he was making the case that stronger induction has its own sort of a priori, a higher level, as it was called, reasoning. Here that's just called superclassical results that ultimately, or many of them, relate to the geometric series, or Zeno's arguments, which weren't mentioned. Yet that the problem, or the riddle of the fallacies of induction, was a key component of Hilbert's account and for the formalization. And this is when he wasn't quite called a formalist yet, because Brouwer was using that as a point to make that it was incomplete and subject to its own deconstructive account that it's unwilling to make. So then Gonseath was introduced as also pointing out that and holding fast to that there must be some kind of superclassical account. And here that there are particular examples after motion and time, that then for structural realism, it kind of goes both ways, that matters of motion and the infinitely divisible, and then for the infinitely divided, so that iota values, these line reals, are already infinitely divided. They no longer have the operation of multiplication, only addition, so that the accounts of otherwise paradoxes and contradictions result to having three distinct laws of large numbers and three distinct models of continuous domains together. that Gonset about weak-strung induction and the accounts of completion and Poincaré are pretty well aligned. And then it was described that basically just Hilbert walked off from that without addressing the kind of finality of it. And then that Bernays walked off with that as if he'd won. So the point there is that Kahle's account of then Gonset and then similar accounts are modern for modern structural realism in foundations, because that's mathematical foundations. Then with regard to physical foundations, what are the laws? Here there's the account of the continuity law and least action, least gradient of a sum of history, sum of potentials, an overall potentialistic theory with regards to the energy in an entelechy, the energy conserved in this space existing. And here for then frame spaces and space frames, there's these inversions. And wave spirals and spiral waves, the unlinear, then for the rectilinear, and all the accounts that have been stacked up today since statistical mechanics after the Galilean and accounts theories of relativity, holding one thing constant and getting a partial result. That these are the reasonings why then for the continuous, like the continuous quantum commutators was put up here. And the Schrodingerians and Einsteinian Lorentzians making models of physics that then when the account was made, for example, in the talk of Greene and Carroll, their kind of manifesto or position statements, as they may be, then the accounts of the interpretations of these theories, vis-a-vis being various and different theories, getting to arrive about that there's one theory and a super Euclidean, super Archimedean, and it's Cartesian and with Poincaré, and then for the Zolfrey metric and these sorts of counts where there are no closed time-like curves, yet there are everywhere closed infinitesimal time-like curves, no closed finite time-like curves. So these sorts of reasonings then make for this sum of histories, which is the current way of things after Feynman and the path integral and the like. Are also of the sum of potentials, the more potentialistic account, which all the electricians and the geometers have had, particularly in the 19th century, for Fitzgerald, and real space contraction. And then the continuous quantum commutators is for accounts of Born's infinite self-energy, or Feynman's de-re-normalizability, and the renormalizable, meaning, again, about infinity and partial quantized accounts. And the particle conceit and these kinds of things make for so that then, thusly, the foundations is a little bit addressed. And then these talks basically reflect the idealistic tradition in the structural realism, these modern sorts of accounts that are bringing back together the things that logicist positive abandoned for itself, but then forgot, and then had to recognize that it's only science, at best, science, and science at its best, at best. Stronger logicist positivism. That then the structural realism is for natural infinities because there's natural continuity, and it is so in any kind of sense of reasonable, logical causality is inviolable. Then the idea here of Bohm and de Broglie is basically that the ghost wave or pilot wave is an account of that there's infinite in the doubly infinite speeds about quasi-invariant measure theory, because mathematics says so. It does structurally in a structure. And we still have a schema of it, and after the re-Vitali-ization of measure theory for the measure problem, and getting to help resolve the, as it might have been Menachem Magidor's mention of the giant monster, or the monsters of independence. Here are the giant monsters of independence since Erdős of integer theory, for this great atlas of mathematical independence. Foundations that mathematics is physics, so that it's not wrong or blind. So that's what I thought to mention briefly before I get into the box of books. Variational principles and free boundary problems. Avner Friedman. A volume in Pure and Applied Mathematics, a widely inter-science series of texts, monographs, and tracts. Richard Courant, founder, Lippmann Burrs, Peter Hilton, and Harry Hochstadt, advisor editors. So Courant, of course, is famous for Courant and Robbins, and then the kind of free boundary problems is going to be developed in this book. And now variational principles are the virial principle, or the hypothesis of small perturbations, is the account of for things like Monte Carlo, and relating that to Markov chains, and the ergodic is accounts of when there's a boundary and that's a singularity, and so it's undefined which way it goes, to assume a small difference and then guess that it goes one way or the other, and then making for the usual counts of gradient descent and for principal component analysis or component analysis, and then saying the component analysis is to introduce a small perturbation, the variational or the virial, and then that technique is used in a couple different settings. So the variational and the virial and the which is like life, like it just moves, or the small perturbations it's moved. These are counts that are kind of common with the various applications and definition in various fields. So this book, with other books in this series, being like numerical solutions of PDEs, Fourier series and integrals of boundary value problems, and so integrals of boundary value problems, and then Green's function and boundary value problems from Wiley Inner Science. Then has this book, Friedman has. Then there's also quite a few other tracks in this series. Geometric Algebra, Differential Games from Friedman is another book by perhaps the same author. A Course in Modern Algebra, The Functions of Mathematical Physics from Hochstadt, Kobayashi and Nomizu, Foundations of Differential Geometry. See, differential geometry here is with symmetry, submergence, and sheaves is a subfield of mathematics. And the problem is it absconds with the definition of function and says that that's like so, but non-standard functions besides just complete and total functions are a bit beyond differential geometries. And then, Melzek has Companion to Concrete Mathematics. So that would be like Graham-Patashnik and Rao, or Graham-Knuth and Patashnik with Concrete Mathematics. They have this great book after Dr. Knuth's The Principles or the Art of Computer Programming, and its addenda and its fascicles through volume 4 or so. That's in Concrete Mathematics, explaining why binary things that happen in computers also have their analytical properties for arithmetizations and the like. Concrete Mathematics, I'd imagine that those would be related. Perturbation methods, so perturbation methods, variational principles, the virial principle, hypotheses of small perturbations, all kind of the same thing. Nonlinear operators and differential equations in Banach spaces. That's kind of after assuming that then the things are smooth. After it's kind of a granular and a finitistic approach. Then how then the algebra is okay to continue. The operator theory, the operator calculus. Linz with a theoretical number analysis, numerical analysis, and an introduction to advanced techniques. Many of these things would be found as old wrapped as new in many modern approaches today. So making a survey and then try and find all the techniques and the methods and these sorts of things is a way to go to make it so that then there's more than a grab bag assortment of tools in the toolkit for differential analysis, that there's a perspective on the differential and the integral analysis, and the singularities and the boundaries and these sorts of accounts, as talking about the integro different integro. And here with regards to Duhamel's principle, it's considered central in that there's a term in the middle. It's nominally zero and neglected in almost all accounts. It's nominally non-zero in an account that's not an approximation. Abner Friedman, Department of Mathematics, Northwestern University. The preface from the author reads, in part, important developments in the study of free boundary problems have been achieved in recent years by introducing variational approach wherever possible. This enables one to conclude without great efforts that a solution to the free boundary problem exists in some weak sense. One can proceed to establish the regularity of the solution and then hopefully study the smoothness of the free boundary itself. In fact, within the last 5 years, significant methods have been developed for analyzing the free boundary, and this theory has now reached a certain stage of maturity. Its future looks even more exciting. An increasing number of physical engineering problems are becoming accessible to this growing body of methods. It is therefore an appropriate time to discuss the main developments of the field in a systematic and self-contained manner. Since some of the main developments were motivated by physical models, we have kept close contact between the general theory and applications to physical examples. In order to make the book more readable by graduate students and non-specialists, we have included in the text the detailed statements of the standard theory of elliptic and parabolic operators that is being used. This is done more systematically in the first 2 chapters. So such sort of account of operators then are also relevant to the theory of fields, modular fields. And these and the like, and then about the openings, perestroikas, and catastrophes, or here the free aspects of the boundaries or the singularities, or for integral equations, they're envelopes. These are this is where the sidewalk ends and where it continues, and these sorts of things. That being that where the sidewalk ends was a children's book from Shel Silverstein about a regular, ordinary, normal world with a sidewalk for conveyance, and where it ends, and that was the end of the world of a flat Earth. But yet at the same time, it was the thought of it, where it is. Copyright 1982. So it talks about existence and regularity. So there's the existence, uniqueness of solutions, and then regularity with regards to realities and regularities and these kinds of things. General theory of existence and uniqueness. W2, P regularity for the obstacle problem. So this is discontinuities often enough. The filtration problem, the elastic plastic torsion problem, parabolic variational inequalities, the Stefan problem, S-T-E-F-A-N, Stefan, variational inequalities for the biharmonic operator, and thin obstacles with regards to layers and media and boundaries, barriers and boundaries, and the boundaries and the envelopes of these things. The Hodograph Legendre transformation, analysis of the free boundary, then he gets into convexity properties, so geometrical, using accounts of geometry to make cases for sandwich and limit theorems and the like. Regularity of the free boundary, the shape of the free boundary for the Stefan problem, stability of free boundaries with singularities, page 256, and then bibliographic remarks. Then there's jets and cavities, so this is for dynamics, and then for resonance theories and the like, and also then for torsion. Jets with gravity, the continuous fit for the gravity case, page 379. Variational problems with potentials. So the potentials would be the tendencies and propensities, either in both. So introducing a variational principle often is giving a propensity to what would otherwise only have tendencies. It is figured that tendencies are what equilibration is naturally equilibrating all the time toward equilibrium. It's its tendency. And propensity is any dynamic or act that acts on those. So mathematically, variational principles or virial principles or perturbation theory introduces interferences or that it interferes with the system of these mathematical objects. And so that's a propensity. It's given, it's propelled, the idea being. And so that's just helping to establish that in between tendencies and propensities, otherwise it's kind of being the same where it goes. Like for histories and potentials, they're sums. Or for oscillation and restitution, it's periodic. Yet how does it go back and forth, since it crosses the line in the middle every time? And then the attenuation and dissipation is like it goes away. Does it ever stop? Is there a floor in these sorts of accounts? The tendencies and propensities is the idea to explain. Otherwise, the causality in these sorts of accounts, the continuity. And this has that, like I've mentioned many times, and we'll continue to mention that in Sadov's macroscopic theory of matter, the system of constituent relations and it always includes a continuity term and a gyroscopic term to help reflect upon these sorts of principles. Variational problems with potentials, then. Vortex rings, structure emergent, the Thomas Fermi model. This is about I'd imagine it's related to things like the electron-holes, Fermi-holes, being an entirely different thing that are resolved in solid-state physics to be electron-holes, which then for Linear Weichert, the entire account of the statistical mechanics of electrons for E and M is made that way. that it's further described and has properties outside that theory in Fermi's theory, Fermi, Fermi. So in free boundary problems, not in variational form. So these would be examples from the grab bag toolkit of a closed kind of forms. Holder continuity, growth and Holder continuity, HO umlaut LDER Holder. It's got the Holder inequality as after Cauchy-Schwarz and the triangle inequality. It's a great thing in functional analysis and these sorts of things. The two-phase Stefan problem, again, kind of like when talking about the weak and strong induction, kind of like weak Stefan and then the higher level and strong Stefan. So free boundaries with singularities on page 256. Assume non-decreasing function satisfies the assumptions. Integration by parts. Energy identities and potential estimates. So page 256. Page 296. Has the free boundaries with singularities. Let omega be a convex domain, meaning it's got the property that there are points on it that are nearer than the line in the surface, in the domain. So it's any account of introduction of tension or contraction with the idea that there's a particular cusp of a convex domain or cusps. Domain in R the N, so multidimensional real space, with C2 boundary, so that would usually be the complex plane squared. And here there's the complex a diagram for left-right complex numbers, because division, the operation in complex numbers, is defined one way and there's another way. And so factors and products and roots in complex numbers are not unique. One may aver. In the usual account, after the deMoivre's account for the Euler's identity, which makes Gaussian complex analysis, which is used all over the place in mathematics and physics, which I call Eulerian Gaussian complex analysis, instead of like the Cartanian with reflections and rotations, because that's all they use are the same parts. If like they were making two different interpretations, they're two different theories, but they all live kind of on the same diagram in the middle. I believe that was so. Or this here, the C2 is otherwise the C2, because this is not written in the usual sort of typesetting of the thing. It's from 1982. This would be continuously differentiable twice, in which case I had otherwise feel bad to have introduced that aside about what's considered the space of the numbers, the boundary of this domain. Symmetric with respect to x sub n equals 0. So it's like the cusp, the symmetry is what it is. We identify that the next lower dimensional space with a hyperplane, x prime 0, x prime and r of the hyperplane. So it's taken like a projection or a perspective. Here the accounts of geometry have projections, which is like blowing it up, spreading something out, and perspectives, which are narrowing in this kind of sense. Where the x prime is a list of points in the lower dimensional space. Let E be an open set in R n minus 1 intersection omega, so this is where they cross, and let F be a closed set in R to the n minus 1 intersection omega, such that E is a subset of F. So it's got an open set and a closed set, and then the open set is a subset of the closed set in their crossing. We write these sets as disjoint unions of their open and closed components, respectively. That E equals the union of the E sub i's and F equals union of the F sub i's, and assume that E sub I is a subset of F sub I for any I. So this is establishing that there's a linear independence and there's a linearization makeable off these things, and it's not necessarily so. So that's contrived. It's an assumption. And let phi be a C2 function, so these would be continuously differentiable at least twice. So a C2 function isn't necessarily not a C infinity function. It's just differentiable at least twice. before being non-differentiable. And so it's of among the class of continuous functions. So here, this model doesn't have a model of continuous domains. It's just continuous functions and then topology's account of open and closed. And then R is given as a continuous domain. That's the only one that there is. Here there are others. And so that's just making the account then here why then this assumption has various accounts why those are still openings, catastrophes, and perestroikas with regards here to this account of the singularities. Because singularities in a singularity theory are branches in a multiplicity theory. Like the aforementioned Eulerian and Gaussian, it's just a branch. There are others and these sorts of things. So phi is, sometimes people say phi, I'll always say phi for the Greek letter, phi. Let phi be a C2 function in omega bar, phi less than 0 on partial d of omega, and denote by u the solution of the obstacle problem, the integral over the omega of grad u dot grad v minus u, so a convolutive setting, u and v minus u, making that's the difference between them, the product, so that's the convolution operator usually enough, of dx greater than or equal to 0, that for any v and k and for any u and k. So this is that it's convex everywhere, so that's kind of a property that follows from that. Where k equals in this set v in h from 0 to 1 of omega, and then I think that's Hermitian. See, I'm a little lost in the context here, trying to attach these things. But it's something to figure out. That v is greater than or equal to phi. So k here is kind of this cap above it. We denote by lambda the coincidence set, and by lambda dot the exterior of lambda, or that might be gamma. Again, that's lambda, but again, my lack of facility or aptness with the alphabet is showing itself. And the next theorem we established for some phi a disjoint discomposition. So lambda equals the union of lambda j's, and then the lambda dot equals the union of the lambda dot j's. The closed components, the lambda j's, and the open components, lambda dot j's. So this disjoint decomposition is basically is an account that it's still linear in a sense. So those properties then make it so later then you can say, well, now I've got free boundaries with singularities that I'm not saying how it's done, but it is done. So this is just describing what needs to hold. And then he says his theorem 11.1 is let E and F be as above. There exists a C infinity, so the class of infinitely differentiable functions, or smooth functions, or sometimes called them, continuous functions, which just has the property that for any two neighboring elements, they're as close in the range as they are in the domain, or that proximity is maintained, and trichotomy in continuous functions. There exists a strictly superharmonic function phi that is delta phi less than 0. So the harmonic functions are just the Laplace when the Laplacian equals 0, vis-a-vis the usual account of the Lorentzian, where the Laplacian is an infinitesimal, ds squared, the metric, the Lorentzian. And so the superharmonic functions basically then have an account just where the Laplacian is 0. And what that gives is, or the harmonic functions, as regards to a superharmonic function, that would be an extension of definition. Function of phi, that is delta phi less than 0. So it's harmonic, and furthermore, it's taking that again is negative. In omega bar with phi less than 0 on d omega, partial d omega, so the partial accounts, such that for the solution U there holds the decomposition with 11.3 with the relations 11.4. So these are accounts he's already established that for the solution there holds the decomposition that then he's able to make via decomposition. Then, for example, the integration by parts bit mentioned a little bit. It follows that whenever x prime 0, 0 is a point of accumulation of components of f, the free boundary has an infinite number of components in any neighborhood of x prime not, 0. Whenever, so according to topology's account of a point of accumulation or a limit point or a critical point of accumulation of components of f sub I, the free boundary has infinite number of components in any neighborhood, so it's continuous, according to the definition matching a continuous function. Because otherwise, if these open and closed, according to the topologies, that this would be the quasi-invariant in the topology, where otherwise is so. So he's assuming an invariant topology in this sense. It is interesting to compare this situation with the positive result for n equals 2, obtained by reference 138a, see also section 2, problem 6, because phi is a strictly concave function and is homeomorphic to an annulus, and that's like the cusp, the ring or the cusp. And if phi is analytic, gamma is a Jordan curve having analytic parametrization. So that's an account that makes follow then that for the relation to geometrical, it's a simple closed connected curve, and because otherwise talking about these open and closed sets is they're discontinuous everywhere, is kind of the idea. That's not really mentioned here, but it's implied because otherwise they would be closed and open. Clopen. So this gives an example of kind of development, then saying, well, then while these things hold, then our derivations hold, then we can talk about the boundaries and talk about their singularities with the free boundaries. And then he gets into the count where for the analysis, he finds a point where he can find something goes to 0 and thus eliminate it from his algebraic form and have a simpler algebraic form that has, though, an implicits why it is not necessarily closed. Otherwise, when the implicits are satisfied, it's good. When they're not, it's not. If necessary, we get delta V greater than 0 in phi, or in omega. Defining H equals 1 minus delta V and recalling 11.9, the proof of the lemma is complete. So these algebraic derivations make the stack of derivations. They have their implicits and explicits, and the parameterizations and the formulations. And so then finding where then there's a singularity, that's a branch from multiplicity. That's the openings, perestroikas, and catastrophes. We shall next give examples of analytic superharmonic obstacles for which the free boundary has a cusp. See, that's kind of the point, is then saying that then they can do the analysis cetus on that and carry that forward. By the Cauchy-Kovalevsky theorem, this problem has a unique analytic solution, and so on. Here's some bibliographic remarks from the author. The Hodograph-Legendre transformation and the treatment of section 1 are due to Isakov and due to Kinderlehrer and Nirenberg. Schaefer has given the method in problem 3 of section 1. The hodographic Legendre transformations have also been applied to elliptic systems of equations in minimal surfaces by Kinderlehrer, Nirenberg, and Spruck. SPRUCK, not SPRSH. Theorem 2.1 is due to Louis and Stampacchia, or Stampacchia. Theorem 2.4 is established by Caffarelli and Riviere. All the other results of section 2 are due to Kinderlehrer. Results of section 3 to 5 are due to Caffarelli. See also the original proof of theorem 3 appears in reference 56b. The proof presented in sections 4 and 5 is taken from reference 56e. Theorem 6.1 is due to Alt 5a. Alt ALT. The three-dimensional dam problem was first introduced by Stampacchia and Ghilardi. Theorem 6.5 was established by Friedman and Jensen. The results of problem 3 of section 6 are also taken from reference 95b. The results of problem 2 are due to Friedman for m equals 1 and to Jensen for m greater than equal to 1. Another proof of theorem 6.5 was given by Cryer, C or Y E R. The convexity of free boundary for another filtration problem is established by Boyeri and Gastaldi. Filtration problem with several layers was studied by Biauchi, Comencioli, Maginius, and Pozzi, Biauchi, and Friedman, and Benchi, and by Caffarelli and Friedman. In reference 58a and b, the shape of the free boundary is studied in the asymptotic behavior is derived in one of the layers, which becomes very thin. The limit problem is a free boundary problem with mixed Dirichlet and Neumann conditions. Mrs. Torelli. So these are examples of kind of the references in the bibliography and also the authorities in this field of free boundary analysis with the variational principles often, and then with regards to their relations to analytic geometry, analytic function theory, algebraic geometry, differential geometry, geometry is the idea. In analysis. In stochastic control, problems of optimal stopping time can be reduced to variational inequalities. Here I got the stop derivative instead, so it's not a variational problem. It's the stop derivative in these sorts of accounts. About a continuous operator in power terms in both positive and negative numbers, which otherwise does not exist. Well, then let's grab a few more books here and just look at them briefly. Now, this is something I'd be happy to mention, is Motz and Weaver, Lloyd Motz and Jefferson Hayne Weaver. They have the story of mathematics and story of physics. So if you're interested in mathematics or physics and you would like a history describing the developments in mathematics and physics, Motz and Weaver are great. If you have no other books about mathematics and physics, but want to know a lot about it and want to know what people in the field would usually kind of know if they study the history of it, Motz and Weaver are fantastic. They're great. So he's talking about Monge, Gaspard Monge. So this was a Frenchman in the 19th century from the engineer school who is responsible for a lot of stuff going on in the area of long after, yet related to the what goes on with Cauchy and what goes on with Liouville with regards to systems of differential analysis. That Monge then is about that side. These ideas later evolved into differential geometry, which owes so much to Gauss, who did so much to expand Monge's ideas. So Gauss owes Monge, M-O-N-G-E, or Monge, or Monge. I've mostly heard it pronounced Monge. Although Monge presented the basic concepts of projective geometry, it became a recognized branch of geometry only after Monge's most talented student, Jean-Victor Poncelet, devoted all his efforts to the development of projective geometry along the lines of DesArgues' original work. So DesArgues is given a lot of accounts of, after Vietta's formula is the way I see it, and the accounts of connecting to arithmetic, the algebra, the analysis. And then, though, here there's Duhamel is more for Poincaré and Duhamel. And then he talks about like Felix Klein's famous Erlangen program. So before the Hilbert program and before the Bourbaki program or Langlands, Erlangen is better and cooler. The group of coordinate transformations which leave invariant the theorem of Pythagoras, for example, represents Euclidean geometry. To justify his group theory approach to geometry and its power, Klein demonstrated that non-Euclidean geometries are projective geometries with a special kind of Pythagorean theorem. So this is super Euclidean, which is great. Klein completed his investigations of the nature of groups by showing that the theory of groups leads to a unification and synthesis of the various branches of mathematics into a single self-consistent logical system based on impeccable philosophy. So this is then for the group of all groups in composition. That what composes is all one structural realism, which is nice. Through group theory, Klein thus brought mathematics to the peak of rigor that Galois and Abel had sought and Cauchy and his colleagues had continued. So it counts here. Picture John von Neumann. The traffic problem, an outgrowth of game theory. I'd be interesting. He mentions, says von Neumann's main objective in developing a theory of games. What I'm interested in is von Neumann's analysis, because that's the concrete mathematics is a theory of games, but the analysis is something different. Because he talks about the quasi-invariant measure theory and for the re-Vitali-ization of measure, that von Neumann had a role after Gödel showed the independence of the continuum hypothesis. Von Neumann presented another one showing, the non-consistency of the hypothesis, or the consistency of not the continuum hypothesis. And he's usually left out of accounts that then get to model forcing, which is about the independence in the mathematics and the contradictions that anybody could read from them. The non-classical logics, the paraconsistent, which is like, well, it can't be broken all the way. We'll just say it's broken once, and then it's not broken. Non-classical logics, which is an accommodation, yet not really a solution to the things. It has that then the quasi-invariant measure theory and the re-Vitali-ization of measure theory has that von Neumann also has a role in that. Besides, for these matters of mathematical independence, about these superclassical results instead of the accounts in fundamental or elementary theories. Order and knowledge. The evolution of modern mathematics. Planck, Einstein, Bohr, and Schrödinger revolutionized physics, or take the mathematics as it is and simply try to fill in the gaps left by earlier mathematicians. The contemporary mathematician concerned with pursuing significant original research must answer the question whether he or she should try to revolutionize mathematics as Planck, Einstein, Bohr, and Schrödinger revolutionized physics, or take the mathematics as it is and simply try to fill in the gaps left by earlier mathematicians. So yeah, Motz and Weaver is fantastic, and I'd recognize it. Their bibliography includes Eric Temple Bell's, W. Rouse Ball, Motz and Weaver, they're the atomic scientists. Carl Boyer, of course, who's great. Ronald W. Clark's Einstein. Albert and Infeld, The Evolution of Physics. Einstein and Infeld. Kasner and Neumann. Klein, Morris Klein. John Herman Randall, Making of the Modern Mind. And they say Dirk Strunk instead of Dirk Stroik. So Stroik is spelled several different ways. Here they spelled it Strunk. That guy, like with the Mac Tutor Archive and all that kind of stuff. A Concise History of Mathematics. D.E. Smith, Jagjit Singh, Great Ideas in Modern Mathematics. So yeah, Motz and Weaver is good. High temperature chemistry, current and future problems. So in the dynamics, this is a research or trade publication. National Academy of Sciences, National Research Council. High temperature chemistry, current and future problems. Flyer from a monthly journal of poetry. That's nice. A conference organized at Rice University, Houston, Texas. Committee on High Temperature Chemical Phenomena of the Division of Chemistry and Chemical Technology, National Academy of Sciences, National Research Council, with support of the Air Force Office of Scientific Research. 1967, Washington, D.C. Has had as its goal the promotion and coordination of activities concerned with high temperature phenomena and related aspects of materials science. This is like, here's an idea, is like, well, how did they make new modern chips? Well, it's lithography. And then, okay, so it's NAND gates and lithography, and then they got capacitors put in to make RAM. Okay, great. And then, well, what's the technology of that? It's like, well, they got stacks and vias, or now they're working on making all kinds of higher density, and then the mechanical processes. It's like, so they got this laser holography and lithography to make chips out of sand. You take sand, you melt in a very fine, refined block, and then you use lasers and you etch it, as after masking, etching, lithography, and making just a diagram on a chip. And then when you put electricity on one side, it flows through like water and makes a chip. So anyways, then the idea is like, well, how do you make it so like the indium gallium arsenide, get them all organized? And it's like, well, you kind of like, you put it in as an alloy, and then you separate it according to transitions and heat and stuff like that, so that it pushes all the indium on one side and the gallium on the other side, the arsenide in the middle, or how it works. So then it can make, according to these wells that can be drilled in by just laser lithography and holography from all three directions at once, to make the little melter pots just kind of embedded in the thing. So you just take layers of silicon and layers of dopant, layers of silicon, layers of dopant, and then it works out. Then the manufacturing process can make it then just like, you just lays the block, and it makes the big giant chip. And so the high temperature application is like, well, how high? You know, and these kinds of things. Re-entry, ablation, and weight chemistry of polymers, composites, and refractory materials. So this is like how you know, the space shuttle's tiles were figured out and stuff like that. Which were always falling off, is the idea. But they had to, because Earth entry, reorbit, is considered a very hot experience. Areas in which more high-temperature phase equilibrium research is needed. By A.M. Alper from Corning Glassworks. So they got the silicon figured out. Further research is needed concerning liquidus temperatures above 2,000 degrees Celsius in binary systems, in particular in ternary and quaternary systems. these sorts of things. Principles of radiochemistry. So radiochemistry involves the chemical properties of radioactive materials. H.A.C. McKay, M-C-K-A-Y, McKay. Radioactivity, radiochemistry in a systematic and critical fashion. Applied Chemistry Division, CRC Press, the Chemical Rubber Company, publishers of the Handbook of Physics and Chemistry. The aim of this book is to treat radiochemistry as a whole in a systematic and critical fashion. So if you're interested in radiochemistry, then you'd probably be familiar with this book, as it's the textbook. The author would like to thank colleagues at the Atomic Energy Research Establishment for advice and comment, in particular W. Barr, J.G. Cunningham, J.R. Finlay, Mrs. K.M. Glover, I.L. Jenkins, E.S. Lane, N.R. Large, A.D. Leclerc, H. London, and G.N. Walton, as well as P.E. Glentworth of Leeds University and C.E. Mellish of the Radiochemical Center, Amersham. So this has general references. It says classics are radiations from radioactive substances or Rutherford. Rutherford is a giant in physics and deserves a lot more credit than he gets. Applied radiochemistry from Otto Hahn, I imagine, 1936. A manual of radioactivity. Radioactivity applied to chemistry. General radiochemical textbooks. Chopin, Linder, Schmeiser, Jenkins, Hasinski, Carswell, and Wilson. Textbooks of nuclear physics and chemistry. Harvey and Cunningham, Friedlander, Lefort, Williams, Bertram, Segre, and Fremlin. General books on the chemical applications of radioactivity. Isotopes. So here after Sachs for Slater for structural chemistry and Sachs for nucleonics and nuclear theory. Those are considered largely underserved by the usual accounts of atomic chemistry and atomic physics. Ionic polymerization, unsolved problems. Furukawa and Vogel. Decker, D-E-K-E-R, publishers. Signed by the author. First Japan, U.S., or Vogel. First Japan, U.S. seminar on polymer synthesis. Polymer synthesis. So vinyl, usually, making vinyl, making all sorts of then textiles and these sorts of accounts. Here there's been read some other books on ionic polymerization and the accounts of the chemistry involved in that. It was once said that in the field of chemistry that 2/3 of chemists were employed in making vinyl. You know, because that's all the plastic in the world, in a sense. Here's this book called Faster Than the Speed of Light by Joe Maguire, The Story of a Scientific Speculation. Now, I sometimes I confuse Maguire and the account of the tired light, or as Finlay-Freundlich put it, the theories in the physics today, that this is a story, he says. It's from 2003. So what I mean by that is I've confused that with another physicist, and so I just when I'm talking about the theory of tired light, here it's redshift bias distortion and redshift bias removal for accounts of occult Fresnel, that Fresnel is a giant in optics. And so that makes for explaining dark energy away, because it just takes a long time to get here to the light, because as it enters a rotating frame, it has to go around to get into the focus, is the idea. So he says he's got a speculation. He talks about the success of relativity. The geodesics, here there's the orbifold, because it's the sum of potentials instead of the geodesy, which is the sum of histories. It's the same thing, it's just the opposite way of looking at it, in projection and perspective. So these are the ideas. Talking about Moffatt and Lorentz invariants. and then Einstein's launch of Moffat's career. And then he said that Einstein was still working on a theory of everything. But Einstein did give like the outs for the centrally symmetric to make for real space contraction. So Einstein just kind of walked back his theory a little bit. Kind of like when Carroll and Greene were talking about Newton, they took pains to say, well, Newton wasn't wrong. You know, so that later then when you look at their theories, you could say, well, we weren't wrong, you know, well, they just weren't kind of right. And then the idea then that Einstein was troubled at the end because he wanted to have a total theory is like he had reached the limits of what the mathematics of that can do. And then he also gave an account in Out of My Later Years, Einstein's great final word on these things. Why that is so, and is a great thing. So I guess that's the end of the box of books for today. Didn't quite get through all this box of books, but I'll pick up from that briefly when I get there. So then this last little thing is Steinberg's 500 years of printing. So it's about the development of the printed word, and that these days is any kind of account of text, for example, in the digital. So this has just got the history of since Gutenberg and the like. The printed word, 500 years of printing. Good day, gentle readers. Reading foundations. It varies.